All right, so we're going to take a look at systems of equations. So we're used to dealing with a single equation. So a single linear equation here, right? All the points on this equation represent a solution. And if we take those values and plug them into the original equation, we'll get something true, okay? So in a system of equations, what happens is you have more than one equation that has to be satisfied at the same time. So let's introduce a second equation, and then we will now have a system of equations. So we've got this. So I have two equations in my system of equation. So let's think our way through this. On this red line, all those points on the red line are solutions that satisfy the original equation. And if we look at the second equation, all the points on this blue line satisfies that equation. But if we want to take both into account at the same time and find a solution that satisfies both of these, well, then we would want to find something that is a point on the red line, so it's a solution to the first equation, and also is a point on the second line, so it's a solution to that equation. Well, we see that there is such a point. This point of intersection is the solution to this system of equations. So you want to keep that in mind, like keep this picture in your head, because later on in this chapter, we're going to be doing most things algebraically, and it's easy to kind of lose track of what you're actually doing conceptually, and you're just kind of trying to follow steps, but it's easy to kind of go, I don't really know what I'm doing, I'm just following these steps. But if you can keep these pictures in your head, then it's easier to remember why you're doing that step and what that step actually means. So just remember, when we have a solution to a system of equations, it means that's the intersection point of those two lines. This point should satisfy both of these lines. So let's graph it on there, and we see that point there. So 2, 1, that's the ordered pair representing our solution. So an x value of 2 and a y value of 1. And let's see when we plug them in. So when I plug in 2 for x and 1 for y, I get that 1 is equal to 4 minus 3. Yeah, that's correct. And when I plug in here, I get 4 plus 3 equals 7. Yeah, that's correct as well. So we can verify that this is, in fact, a solution to our system of equations. Now, anytime you ever do a system of equations, you want to check it the way I just did. It's very easy to make a mistake, right? Especially when we're doing things algebraically. You'll get an answer. Your answer may just be completely wrong. So you want to take the time. It does, as you see, I just went through it. This one we could even do in our heads. It didn't take me very long to check it, but you can save yourself a lot of time and frustration if you go through and verify that you are in fact correct, because there's lots of mistakes that can be made along the way, and we'll just want to double check we didn't make any of those. Okay, so this is what's going to happen like 95% of the time when you do problems, is you're going to end up with one solution that is an ordered pair representing an x value and a y value that satisfies all the equations in your system. It satisfies the system of equations. I want to show you one drawback to solving these things graphically. What you'll find is that we generally are going to solve systems of equations algebraically. And you might go, well, why? If I have a graphing utility that will graph them for me, why wouldn't I just do that? That seems easier than doing a bunch of algebra. And here's why. Let's take this and change this to a 6. And all of a sudden you see the problem. Look at my intersection point. Right? It doesn't fall nicely on some grid lines, so I don't know exactly what that solution is. There's an x value and a y value, and I can kind of go, well, the x value looks like it's a little bit less than 2, and the y value looks like it's a little bit less than 1. But if you're trying to run a business or you're trying to figure out some scientific principle, just having an estimate for where these numbers are isn't good enough. Right? If you're running a business, you want to be running, the most profitable business you can. You want to know exactly where that solution is located. The algebraic tools will give that to us every single time. The graphical system helps us understand these kinds of problems really well. And on certain nice problems like this, then the graphical way of solving these works out okay. Most of the time, that's not going to happen. Most of the time, your solution is going to either have fractions or decimals or something like that, which makes graphing it a little bit harder to do. Okay. Now, let's point out a couple things that happen with other types of solutions that can come up. So on rare occasions, you get one of these other types of solutions. And again, it's helpful to be able to have this picture in your head so you can kind of think about it. Otherwise, some of these steps get kind of confusing. So if you can always go back and picture what we talked about in this video in your head, it's going to help you keep these straight a lot easier. So let's take this equation away. So our system will now be composed of this first equation, y equals 2x minus 3, and this one down here, y equals 2x minus 5. And notice this is a little bit different. What do we have here? Well, they both have a slope of 2, right? The 2 on the x, that gives us the slope. So they both have a slope of 2, but different intercepts. This means we have parallel lines. Well, parallel lines never intersect. So if the solution to a system of equations is the point of intersection, then this system of equations has no point of intersection, therefore it has no solution. So when we talk about having no solution in a system of equations, what we're really saying is that our equations don't line up anywhere, right? Okay, so that's one possibility, no solution. The other possibility is this, where we take this equation, I'm going to add this 4x minus 2y equals 6 as my second equation, and it seems normal. It doesn't seem like there's anything weird going on there until we put it in there and we recognize that, wait a minute, this is the same line as the other one. And you can look, if you look at the line, it's toggling on purple and red, meaning these two lines look the same. Basically, what I did was I took this first line and I did some algebra to make it look different, and I got this down here. It's the same exact line, just being written differently. Why would I do that? Well, it's to get an example to show you, but this happens in real life where sometimes you end up with a system of equations where one of your equations is a multiple of the other equation, meaning you really just have two of the same equation. So technically what we have here is an infinite number of solutions, which may seem like that's great news. Usually it's not. Usually it's not as helpful as it may sound, because if you're solving a systems of equations, you're probably trying to figure out, for a business, say, how many units should we produce next month? What should we price our units, our product at? You want exact answers. You don't want lots of solutions, and you have to try to figure out what's the right one. You just want to go, yep, here's where we maximize our profit if we sell it at this value. So this is what we call a dependent system. One of our equations is dependent on the other one. That is, it's a multiple of the other one. So just kind of keep that in mind, right? This is the situation where we have two of the same line. This is where we have two parallel lines, and our conclusion would be no solution.